Welcome again, everyone, to today's Beyond the Scope talk. I must mention a couple upcoming talks. In 2 weeks, we're going to have a why CMAS panel discussion. So we're having a bunch of different kinds of users. They're going to talk about why they use CMAS and kind of what got them to around here. Then in a month, there will be a talk with Hank Lane about TM, possibly EDS with that. So today we have Stephen Buna. He'll be giving a talk on how low we can go. So some low KV imaging techniques in the SEM. Steve's a research associate at CMAS, and he's also one of the SEM instrument managers, primarily in charge of the APRIO SEMs. We generally like keeping these fairly short, so hopefully around half hour or so, and then with that, lots of time for discussion. So if you have questions during it, you can put those in the Q&A or in chat if you have other issues, or raise your hand at the end of the session, and we can actually spend some time talking about this. Steve?
All right, thank you, Dan, for the introduction. Hi, everyone, and thanks for taking the time to attend my discussion topic today. So as Dan mentioned, today the title of our presentation is SEM Limbo, How Low Can We Go? So that's the general sense. So we're going to talk about beam energy and electron microscopes, and then we'll go through some examples. Dan already mentioned this is intended to be relatively short, so if you have questions, you can submit them throughout the presentation, or you can hold it till the end. If you have any problems with the technology, feel free to mention it, and we'll have one of our panelists try to help you with that as we go. So we always like to do an ad for CMAS at the start here. If you haven't been to our facility before, we have quite a wide variety of capabilities. So we've got 6 different types of transmission electron microscopes, including 2 cryo-TEMs, some dual beam instruments that we can do some sample manipulation with, as well as 4 of our scanning electron microscopes. The 2 in particular that will be emphasized today are these APRIO SEMs that are configured especially for low KV work. We also have some X-ray based analytical tools like X-ray microtomography and X-ray diffraction. So if you have a use for some or any of these other techniques, please feel free to reach out and see what CMAS might be able to help you with. So a little bit about me. If you caught my previous webinars, you would have seen this as well, but I was born and raised essentially outside of Chicago. Spent some time going to school, a few years at Northern Illinois University, doing my bachelor's and master's degrees in physics. And then I did my PhD in material science at Michigan State, and then came to Ohio State in 2013, originally as a postdoc. And then in 2017, I joined the staff at CMAS, and so that's where I've been since. I'm going to skip part 2. That was my affinity for puns. If you caught my talk, the last one, I think over the summer, and we'll skip right to part 3, which is that over the pandemic, discovered a new hobby of rock hounding and rock tumbling. So if you weren't aware, the state mineral of Ohio is flint, because we have some pretty rich flint deposits right about an hour or 2 from Columbus. So over the summer, went out, my wife and I, and collected about 100 pounds of different stones. You can see some examples here. You get very colorful types of formations. So if you're interested in that, you can look up where to go in Ohio to gather your own flint. It's an interesting hobby, and one that I've enjoyed over the last several months. So for today's presentation, we'll talk about beam energies and how that affects things like imaging and microscopy. And then we'll start talking about low energy beams in the SEMs. So we'll begin with what's familiar, and then we'll talk about how it's different when we're dealing with low energies and how that affects our imaging and analysis options. So in general, in the microscopy world, we're used to thinking about just SEMs and TEMs being way up at 300 keV. But when you take a bigger picture perspective, you realize that there are much higher beam energies out there in these particle colliders. So when I was an undergraduate student at NIU, Fermilab is not very far away. So I had an opportunity to participate in a research project there as an undergraduate, where we did some calibration of detectors and analysis of data collected at CERN in 2006. So the scale of everything with high energy particle colliders is much larger. So these get up to 1 million keV. That's a tevatron type energy range. The collaborations are huge. So this is about 165 authors. I lost count after the second page. And then the facilities are also quite large. These are kilometer scale rings. And this is the old bubble chamber at Fermilab, and there's me for scale. This is decommissioned now. They have this whole building converted into offices and other types of labs, but the timelines are also different. So the data were collected in 2006, analyzed throughout the years after that, and then published in 2012. So all of this is very large energy, very large scale experiments. You can get down to the sort of intermediate range, high energy for electron microscopy, but these TEMs are a little bit smaller. You don't need quite a kilometer scale facility, but you still need about a whole room dedicated just to operating this microscope if you want to get at or above specifications. And then all the way down at this other opposite end of the spectrum, where we're going to be talking today, these are much more approachable types of instruments where it's a little bit bigger than a desktop computer, and we can operate these from about 0 to about 30 keV. So about 5 or 6 orders of magnitude lower than what I started out doing as an undergraduate, but still a lot of very interesting research that you can do. So, okay. So this idea of accelerating voltage in electron microscopy, as I mentioned, we're going to start with what's familiar, and then we'll switch over to what's different about working at low voltages. So if you've done anything with SEMs or studied SEMs before in any capacity, you've probably seen a diagram that looks like this, where we talk about when a beam hits the sample surface and then how that energy is dissipated below the surface and the types of signals that are generated. The energy of your beam is important because before it hits the sample, you have the beam traveling through the column. And so the energy of the beam determines what strengths of lenses you need in the column, what types of aberrations are most prevalent, how hard is it to actually get a good image. And then when the beam hits a sample, especially in the SEM case, the energy of your beam determines how big this interaction volume is. And ultimately, it affects the signals that come out of the sample. And so when you're doing your imaging and analysis, what kind of resolution can you get? What type of signals do you have coming off the material? Okay, so beam energy is very important as for all parts of this microscopy process. You've also probably seen a diagram that looks something like this. This is Monte Carlo simulations of beam electron paths in a sample. This is a carbon at 1, 3, and 10 keV. You can see pretty clearly that the interaction volume below the sample surface is not a linear function of beam energy. In fact, it scales something like energy to the 5th power. So going from even just 10 to 9 keV, you would have a pretty dramatic difference. But the point here is that as you get to really low voltages and really low beam energies, you end up getting extremely localized information about the sample. Whereas at higher voltages, you have signals generated from much more significant lengths below the sample surface, as well as laterally away from the initial point that the beam hits the surface. So you can see here, this is carbon. It's a relatively low density material. And so the scale here is going to be different for different materials, but the general trend holds regardless of the material and the beam energy. So if you go from say 30 to 100 or whatever you may choose to do instead of these values, you'll see a similar difference as you go up in energy and change from one material to another. So before we start talking about how our low energy beams affect our signals, we need to first make sure we're all on the same page about what types of signals that we pick up in an SEM, for example. So as a very basic way of describing them, we split them into 2 categories, our secondary electrons and our backscattered electrons. So we can draw a cartoon like this, where you have the intensity of a signal as a function of energy. And so this is a logarithmic scale. In general, you can define a semi-arbitrary cutoff of about 50 electron volts. So any signal that leaves the sample surface with energy at 50 electron volts or below, we'll call a secondary electron. And then everything else we'll lump together and call it a backscatter electron. Okay, so we'll talk about those each separately. So we'll start out with the secondary electrons. These are produced when the incoming beam interacts inelastically with the sample, generally speaking with the electrons in the sample. So put an asterisk there, and we'll come back to why that has an asterisk. But we mentioned already, there's a sort of arbitrary, almost arbitrary, not exactly arbitrary, cutoff at about 50 electron volts. In reality, we see the peak here is closer to about 10 or 20 electron volts. And so the vast majority of the signal coming off the sample surface is at these very low energies. And because those signals have such low energy, they don't move very far inside of a material. So The only ones that reach the surface and then escape into the vacuum and then are detected are the ones that come from very close to the surface to begin with. And that makes them very useful for things like focusing and then determining what kind of topographic features we have on the surface of a sample. Those low energy signals are also vulnerable to deflection, which can be helpful or parasitic depending on if you're dealing with charging effects and you want to get rid of charging halos. That's a downside to the deflection. But if you want to intentionally funnel those electrons in a specific direction, then you can easily do that by using some effects like voltage bias. So because of the way these signals are generated, they have this energy range regardless of the beam energy. So secondary electrons are always going to be about 10 electron volts just due to the nature of how those processes work. So we showed interaction volumes scale with a beam energy to the 5th power, but secondary electron signals are always going to be right down in this energy range. See, the value of the high end here is not defined, so we'll talk about backscattered electrons on the next slide. But to get to this asterisk here, secondary electrons, we lump them all together, but in reality, you can define up to 4 different types. This first type is these SE1 signals, which are resulting from the beam interacting with the material directly below the spot on the sample where the beam hits. So that's really the one we want. That's what matches this initial description, where we have the incident beam, we have our sample, those things interact and they tell us information about that material. That's the part we really care about. We also have what we can call SE2 signals, which are produced by the process where these other backscattered electrons that we've already established are at much higher energies are also moving around inside the material. And as they move around and exit the sample, they also generate their own secondary electrons. And so that's what these SE2 contribution is. And because those backscattered electrons are moving around below the sample surface, the area of the sample where you get signal from is much wider. And that's going to vary with the beam energy a little bit. But in general, these SE2 signals are still useful. They're just not as well correlated with the original spot on the sample surface. And then the SE3 and SE4 signals that are produced, those are much less useful. As those backscattered electrons leave the sample, they end up hitting other things in the chamber. So you have the pole piece, you've got your detectors, you've got things in the column. And so those signals have nothing to do with the actual sample, but they can still be detected. And so they contribute intensity, but no useful information. Okay, so the different types of signals that we deal with, and it's from the secondary electron component. Now this backscattered component, we defined it here as everything above 50 electron volts. So you have a few different types of contributions. You have Auger electrons, you have some plasmon processes, but in general, most of what we think about as backscattered electrons are these quasi-elastically scattered components, where it's information that is relevant to composition. So you have your Z contrast information, and then structure. So things like channeling contrast, if you have a polished metal surface, and then backscatter diffraction. That's all generally happening with these relatively high energy quasi-elastic scattered electrons. Okay. So again, in the context of what we're familiar with, and then how we can think about the impact of changing our beam energy and interaction volume. If we're doing backscattered electron imaging in a conventional sense, we can imagine some cross-section view of a material where you have a two-phase composition and precipitates within this, so these alpha phase within the beta phase, and you can have different orientations and different size particles at different locations. So if you work at a 20 kV accelerating voltage, for example, and you're thinking about the interaction volume below the surface and then what signals you end up picking up, this would be, from a top-down perspective, what you might expect to see in your backscatter signal from these types of features. And as we drop down the voltage and you get something that's much more localized, now you can expect that your image is going to shift and look something a little bit more like this. So you'll still see this feature. This one will now be much more localized to just where that exists close to the surface. You won't even see other subsurface features. And then this one, you'll see the actual in the area that's more accurately represented of what you see close to the surface. And then you can anticipate as you go to even lower voltage, then you become more surface sensitive, and you may even start to see things like this topographical contrast as you go low enough. So you can do this in practice. This is on a titanium-based multi-phase material, and you go from say 30 kV to 15, and then to 5 and down to 2. You can see that trend plays out of fuzzy-looking, blurred images because we're getting a lot of subsurface information. And then as you get lower in voltage, eventually you get to the point where you get pretty well-defined boundaries between the phases. And then you go too low, really, and now you start to see some surface defects. So if you're doing some type of analysis where you want to understand what's kind of the areal density of one phase versus the other, this type of image would be the best one for segmentation. For example, whereas here you're starting to see contrast from features on the surface that aren't really relevant to the microstructure as much. And then these images aren't really useful because you've got so much subsurface contribution. So there's kind of an optimization as far as the amount of decrease you want to use when you're doing your low voltage imaging here. This is still relatively high voltage in some sense, but for backscattered imaging, this is one of the situations where 5 kV is kind of a sweet spot. Okay, so we can go back to the original question and say, how low can we go? If we're talking about humans, well, the world record for limbo dancing is 6 inches, believe it or not. This is set by Dennis Walston, who you may know better as King Limbo in 1991. If you're curious, you can go look up the Guinness Book of World Records, 1992 edition. It's on page 184. But if we're talking about SEMs, the answer here is as low as you want. So the microscope will let you set it as low as 20 electron volts if you're at the right conditions, but you can actually force it even lower than that, and you can invert it if you really want to. This inverted type of signal is what we call an electron mirror. You can do it accidentally if you put a charging sample into the microscope, so like a inverted styrofoam cup, and you try to image that, you'll basically just see a reflection of what's inside your chamber. But you can also do this on purpose, and this is what's used in service mode sometimes if you have issues with your in-column detectors. So this is an example of some debris got onto the in-column T1 detector on one of our aprios. And by making a lens mirror with a negative landing energy, we're able to see there's a distortion here. So there's clearly something on the detector surface that's not allowing us to use that detector properly. So, okay, so now we can think about how is it even possible to get a 20 electron volt beam? And there's a couple components that go into this. And one of them is this idea of stage bias. And so what we can do, this is a relatively old concept that's become a lot more standard now. So you may have heard of it described as beam deceleration or even as a cathode lens. But essentially you can take the pole piece of your microscope and then the stage or the sample and apply a voltage bias between them. And what ends up happening is you create an electric field between the sample and the pole piece. So this is separate from anything that happens inside of the column. This is happening essentially just outside of the pole piece. And so what will happen then is that the beam is generated at the source, it comes down the column, and then right before it hits the sample, it's decelerated to some different energy. And so it depends on the strength of this voltage bias here. And so there's a minimum required energy to generate a beam and extract electrons from the source, and that is typically about 200 volts. So you can only go to about 200 EV unless you use a stage bias to lower it down even lower. So in order to get to 20, you have to have 200 EV and then take off 180 volts. And that's what the Aprio SEM will let you do just automatically. If you want to force it lower than that, we have to go into the service mode option, and then we can override that, and we can send it even lower and invert it if we want to. So it's important to understand that now we have to define something different, because the beam energy here is different from the landing energy here if we have stage bias on. And so if you're not familiar with this, if you've never used stage bias before, then you may not realize it, but in Thermo Fisher SEMs and FIBs that have this option, what you choose on the interface is always the landing energy. So if you have stage bias on, then the actual source voltage is going to be different from the landing energy. So we'll talk about that again as we go through this next few slides, but also want to point out that if you have, say, a retractable detector inserted, and you have something like a 4 kV bias between the sample and your pole piece, if you get too close with your sample, you can run the risk of approaching the vacuum breakdown, and you can arc and fry your backscatter detector. So it's another reason to be careful about your working distance when you have your retractable detectors inserted. So keep that in mind if you're someone that wants to use stage bias with a retractable backscatter detector. So for any particular landing energy, we can set different combinations of the initial beam energy and the stage bias. So landing energy is not a unique parameter. So instead, we can define an additional term called this immersion ratio. And this is the actual beam energy at the source divided by our landing energy. So regardless of what our stage bias is, now we can account for each unique combination of stage bias and beam energy that will give us whatever landing energy we want. So in the case of, say, 200 electron volts landing energy, we can have a beam energy anywhere from 200 up to 4,200. So our immersion ratio can be anywhere from 1 to 21. And that's a unique way of determining and letting us know what was the actual stage bias for that particular set of experiments. So in addition to the stage bias, it helps a lot if you have special column optics like we have on the Aprios. So in these types of instruments, you can help with the fact that when working at low KV, these low energy beams are especially prone to aberrations, and chromatic aberrations in particular, where the difference in energy divided by the total energy is sometimes quite large. And so to help with that, these types of columns have what's called a booster tube, where after the beam is generated, it adds 8 kV in the case of the Aprio SEM to the beam. And so while it's traveling through the column, it is actually at a higher potential. So we say we start at 5, and then now we're in here at 13. So we reduce significantly some of these aberrations that you might otherwise experience. And then right before you leave the column and enter the chamber, you take away that 8 kV signal or 8 kV boost and return it so that it hits the sample at the original 5 kV. Okay, so that really helps reducing some of these chromatic aberrations. And then you also have the benefit of this 8 kV final lens pulling signal from the sample back up into the column. And so now you can use some of your in-column detectors with geometric filtering to isolate the very low energy secondary electrons. So only the SE1 and SE2 signal, and all the other stuff gets blocked. So that's a very helpful way to isolate only the components of the SE signal that you actually want to see. And so you don't need this function in order to get, 20 electron volts, but it helps a lot to avoid some of these issues. So you'll always get a little bit better image quality if you have a booster tube in your microscope than if you don't. So you can do this on the Quattro and other types of systems, but it's just not going to work quite as well as it would on an Aprio. So to put this all together, if you're trying to run the Aprio at 20 electron volts and you want to use 4,000 or 4 kV stage bias, you're going to start out with your beam at 4,020 volts. It's in the column in modes 2 and 3. It's going to hit 12,020 volts. And then as it leaves, you're going to drop back down to 4,020, and then you'll hit the sample at 20. Okay, so while it's in between the source and the sample, it's effectively a 12 kV beam, and that makes it a lot easier to do all the focusing and everything else. And then you have an immersion ratio of about 201 for that combination. Okay. So that's how we would generate these types of very low energy signals without having huge issues focusing them and getting them to actually form images. Okay, but why do we want to go to 20 electron volts in the first place? Well, strange things happen when you take this energy diagram we drew earlier and you just compress it so that we're only working with signals at this energy range. And usually when strange things happen, that means you can do some interesting science. Now, if you're familiar with materials, especially solid state physics, then you may recognize anything in this single digit electron volt range is where you start to reach the same regime as work functions and band gaps. So this is kind of the realm of quantum mechanics a little bit. So now you become sensitive to things like doping levels. So in this type of image, you see at a landing energy of 3 electron volts or 2.3 electron volts, you can actually pick up contrast from different doping levels in a material. To do this properly, you have to have extremely clean sample surfaces. So normally, even on pretty well clean samples, you'll still have some thin layer of absorbed hydrocarbons or other material. And so you have to have really good quality vacuum in the chamber, even maybe an in situ plasma cleaner or in situ sputtering system to help make sure the sample is as clean as possible. We already talked about having the column optics that you need for this, and then a good source. So if you're interested in this and what you can do with it, this is from a paper from a group in Czechoslovakia or the Czech Republic. So this is, and they call it scanning low energy electron microscopy. The historical acronym for it is just low voltage SEM. So you can do searches for these two acronyms and you'll find a lot of references that talk about ways of doing this. As I mentioned, it's become a lot more common to have these stage bias option built in. So some of the original papers are these convoluted systems where they had to figure out a way to apply a voltage bias to the stage relative to the full piece, and that gets complicated. But in the modern systems, it makes it a lot easier to just turn on stage bias and go to work from there. So to show you an example of some interesting things that one of our former students at CMAS, Ben Georgian, did for part of his dissertation work. This is an example of what you see at low voltage, that the idea of a backscattered electron kind of becomes almost arbitrary, because we said it's 90% of the beam energy, but if your beam is 20 electron volts, then what is a backscattered electron? So you have to start rethinking even the physics of how do these beams interact with and scatter off of the nuclei. So what we're used to thinking about at high voltages is that the more dense a nuclei is, then the stronger the scattering. So this backscatter coefficient as a function of energy for these different elements. And so this is a general thing that's been known about for quite a while. It's difficult to come up with precise rules for any particular element or material at any particular voltage, because as you can see, they vary quite a bit. But in general, you should be aware that as you go down below 5 kV and especially below about 2 kV, you start to see inversion of contrast, so that lower density materials now have higher contrast than more dense materials. And so you can no longer apply that basic rule of, oh, that looks bright in my backscatter image, that means it must be a heavier element. So one of the things Ben did was he spent a lot of time doing a lot of really interesting work optimizing different combinations of voltage, working distance, and current on his samples. And so you can see this play out on some precipitates he has. These are sort of embedded precipitates. I pulled this from his dissertation. He was kind enough to share this with me. So there are different types of particles. And then as you go from 600, 400 to 200, you can see an inversion of the contrast as you look at these, the same structures, same types of structures in different energy ranges. And so when you're above about 500 volts, you get this trend that you'd expect based off of density. But then once you get below 500 volts, now you start to see there's an inversion of contrast, and then you get essentially no contrast between the different phases at about 400. And so you can keep going with this. And so you can see it's a general thing that you'll find at different types of materials. And that's something to be aware of when you work at these low voltage ranges. Another example from Ben's dissertation, this is sort of typical backscatter conditions with the backscatter detector, 10 kV. You've got multi-phase material. You can see contrast from different contributions. You've got some precipitates here that form. And you may have an idea of what to expect. And I tell people this all the time, that just because you see features that have the same grayscale intensity doesn't mean they have the same composition, because you may just happen to have similar density. And so in this case, Ben was able to determine that there are actually, I think, 4 different types of precipitates that form. And when you switch to a different imaging mode, now you can see, for example, these 2 types of features that show up with brightened contrast here end up looking very different under lower voltage conditions. So this is another example of something that you can do and that changes pretty dramatically what you see in the microscope. Okay, so that's the extent of what I was going to present today. If you have questions, we can take those, but this is, again, another plug for what's happening in 2 weeks, and then some different ways you connect with CMAS. So I'll go ahead and take any questions anybody might have.
If anyone has any questions, yeah, just go ahead and put those in the chat or in the Q&A is one of the easier ways to do it. If you want to talk with Steve a little bit more, either you raise your hand now or I always send him an email later on to talk.
So someone asked if the recording will be available. Yes, we record these and you'll have access to it later on from our website.